Hello, students. So, continuing our lectures on complex analysis, we'll start with harmonic functions today. Now, if the second partial derivatives of the variables u and v are continuous, in a region R, that is del square u by del x square plus del square u by del y square is equal to 0, and del square v by del x square plus del square v by del y square is equal to 0. That means the real and the imaginary part. This is now if since fz is equal to u plus iv, so u is supposed to be the real part and v is supposed to be the imaginary part. So the real and imaginary part, to satisfy these conditions, then you can say that these are the harmonic functions. Or in other words, you can also say that if the real and imaginary parts they satisfy Laplace's equation, that is del square psi by del x square plus del square psi by del y square is equal to 0, or you can say that del square psi is equal to 0. This is the original Laplace's equation. So if del square u is equal to 0 and del square v is equal to 0, then you can say that the function fz is an harmonic function. We have all studied Cauchy's integral theorem. It says that if fz is analytic in a region, so in a region R, then any closed contour in the region into this integration, so this comes up to be 0. Now there is actually a converse of this Cauchy's integral theorem, and it is called Morira's theorem. It says that if a function fz is continuous in a simply connected region, continuous in a simply connected region, and this condition is satisfied for every closed contour, then fz is analytic throughout the region. Region R. This is the Morira's theorem. Now next we will do some problems based upon the Cauchy's residue theorem that we have discussed in our previous lectures. So first start with a problem. If someone tells you to find the value of sine pi z square plus cos pi z square sine pi z square plus cos pi z square divided by z minus 1 into z minus 2 dz. How to find out the value of this? So what I will do first, we will write z minus 1 to z minus 2 as equal to 1 by z minus 2 minus 1 by z minus 1. So the integral now is equal to integral sine pi z square plus cos pi z square divided by z minus 2 minus sine pi z square plus cos pi z square divided by z minus 1. So the poles, as you can see, for this integral, the poles are at z is equal to 2, and for this integral, the pole is at z is equal to 1. So and these are simple poles. So by the residue, the sum of the residue into 2 pi I is equal to the value of integral, and the residue for simple poles is equal to limit z tends to a, z minus a of z. So for residue a is equal to 2 as in the first case. So for pole a is equal to the first residue will be limit z minus 2, z tends to 2, fz, that is sine pi z square plus cos pi z square divided by z minus 2 into z minus 2. So these two cancel out, and what is left as sine 2 pi whole square plus, sorry, not 2 pi whole square, sine pi 2 square plus cos pi 2 square. So this gives you the value equal to 1. Similarly, for the pole is equal to 1, it will be, residue will be limit z tends to 1 sine pi z square plus cos pi z square divided by z minus 1 into z minus 1. So these two will cancel out, and so residue will turn out to be limit z tends to 1 sine pi z square plus cos pi z square. So again it will be sine pi 1 square plus cos pi 1 square. So again the value will be equal to 1, and the value of the integral sine pi z square plus cos pi z square divided by z minus 1 into z minus 2 dz, according to residue theorem, will be the sum of 2 pi I into the sum of the residues. The residue in both the cases are 2 pi I are 1, so 2 pi I 1 plus 1, so that will be equal to 4 pi I. So this is the answer.